Welcome once again to another episode of Dave Does Math from Home. This is part 2 on our series of videos about related rates, which are implicit differentiation story problems. In the first video we did the expanding and shrinking sphere. Our sphere was expanding because it was a balloon. I like the shrinking version of that problem too, though. That's very interesting. Here we're going to do the ladder problem. The ladder problem is pretty iconic among related rates. It shows up a lot. I've never seen a calculus course that didn't talk about the ladder problem. The ladder problem is the ladder is leaning against a wall. The base is being pulled away from the wall at a constant rate, 0.8 meters per second. How fast is the top sliding down the wall when the base is 3 meters from the wall and when the base is 4 meters from the wall? So you have the situation with a ladder leaning against a wall. I don't know if that's visible. Maybe I can just do this. Here's a wall, here's the ground. You can tell this is a wall because it has bricks. There we go. Wall. And you have this ladder leaning against it. Here's my ladder. The ladder is leaning against the wall. The bottom of the ladder is being pulled away from the wall, 0.8 meters per second, which means that the top of the ladder is falling. The top of the ladder is sliding down the wall as this thing gets pulled away. So the question is about how fast the top of the ladder is sliding, and the ladder is 5 meters long. I think that is all the information that we have and all the information that we need. I guess we should hold on to these guys. We want the 4 meter mark and the 3 meter mark for this distance. I'm making this picture because I am afraid that I need to erase all of this so that I have room to actually do this math. So if you feel like you're going to forget this information, take a screenshot of the video and have that handy while we do this math. I think I have everything I need here. Goodbye, story problem. Okay, this is our picture of the situation at hand. Just like in the last video, we should, well, I'll say, not just like in the last video. In this problem, we should start with this picture. In most of these problems, starting with a picture is a great idea because that'll help you organize what's moving, what's changing, what's standing still. Pictures are very, very helpful. So the first one, drawing a sphere, is hard, so I skipped that. Here we can draw a ladder and a wall. We did that. That's where you should always start. From there, the next place we should go, just like in the last video, is a relationship between these quantities. Fortunately, we have a pretty convenient relationship between these quantities. We're assuming that this wall is vertical, which means that we have a right triangle here. So I'm going to call this x, and we're going to call this distance y, which means that we have a relationship between these quantities of the Pythagorean theorem. X squared plus y squared is 25. That's our relationship here. When x is 4 meters, or no, we can get to that piece later. We'll just go straight from here into a derivative so that we can look at how these things are changing. Interesting to note that the ladder is not changing in size. So the ladder is 5 meters long, and it's always going to be 5 meters long. It's not going to shrink as it moves or grow as it moves. So the change in ladder length is 0. The change in x distance is a thing, so we got to do that. 2x dx will be that derivative there. 2y dy will be that derivative there. The change in ladder length is nothing, so that's just a 0. When I said that drawing a picture helps you know what's changing and what isn't, that's what I meant. Usually there's some part of this that isn't changing, like the length of the ladder or something. That piece gets to stay 0 when you take the derivative. So, I have 4 pieces here, x, dx, y, and dy, and I need to know what at least 3 of these are so that I can solve for the 4th. dx we know. dx is always going to be 0.8 meters per second. That one's fixed. dy is what the question is asking for. That's what we need to solve for, which means I need to figure out what x and y are. X is given. We'll use 3 first. We'll do the x equals 4 case later. We'll start with x equals 3. When x equals 3, we need to know what y is. Y was not given in the problem. But we can use this equation to solve for it. If x is 3, that means x squared is 9. So that means that y squared needs to be 9 less than this. So y squared is 16. It means y is 4. X is 3 meters, y is 4 meters. Hopefully this is familiar as a Pythagorean triple. 3, 4, 5. So, for the x equals 3 meters case, we've solved for y using the original equation, and now we can plug all of this information into here to solve for dy. So let's see what that looks like. 2 times x is going to be 3, times dx is 0.8. Sorry, we'll say 3 meters and then meters per second here. I want to get these units in here. Plus 2 times 4 meters times dy equals 0. So this should be 6 times 0.8 is probably going to be 4.8. Is that right? Yeah. 6 times 0.8 should be 4.8 meters squared per second plus 8 meters times dy equals 0. So 8 meters times dy equals negative 4.8 meters squared per second. And dy, where am I going to fit this? Down in the corner we go. dy equals negative 4.8 divided by 8, which I think should give us negative 0.6 meters per second. Is that even visible on the camera? No, I'll take it. So dy is negative 0.6 meters per second. How can dy be negative? Does that make sense? When you do these problems, you're sometimes going to get negative answers, and you're going to have to ask yourself if that is weird or not. Sometimes you'll get positive answers, and you'll have to ask yourself whether or not that's weird. If dy is negative, that means that y, this vertical distance between the top of the ladder and the ground, y is shrinking. Which makes sense, according to what the situation is saying. If the bottom of the ladder is being pulled away, the top of the ladder is being down, we should expect dy to be negative. So dy being negative 0.6 meters per second, that means that the top of the ladder is falling, y is shrinking. That checks out. We could do this again with our other input. where x was 4 meters instead of 3. So we've done the 3 meter version. Check. We know what the change in y is when x is 3 meters. Let's do the change in y when x is 4 meters and see whether or not it's different. This time x is going to be 4 meters. Hopefully I don't have to work too hard to convince you that in this case y should be 3 meters, because it's still the same Pythagorean triple, 3, 4, 5. And let's plug in some numbers. 2 times 4 times 0.8, sorry, 4 meters times 0.8 meters per second equals 2 times 3 meters times dy. Sorry, plus that equals 0. So this can simplify into 6.4 meters squared per second plus 6 meters dy equals 0. So this will go over there. 6 meters times dy equals negative 6.4 meters squared per second. And dy, I don't know what 6.4 divided by 6 is. 1.6, I guess? No, 1.06 ish. 1.06 and change. Negative 1.06 repeating, I think, meters per second will be the change in y when x is a little further away. So when x was 3 meters away, this thing was falling at a rate of 0.6 meters per second. When x is 4 meters away, it is falling faster. Now it is falling at a little more than 1 meter per second. So the further you pull this thing away, the faster this falls. Which is interesting because this rate isn't changing. We're always pulling the ladder away at the same rate. That's constant. It's just as this distance increases, so does this speed. That's the related rate here. You got a constant rate on one of these with an increasing distance, gives you a decreasing distance here with an increasing speed. Which I think is really cool. This stuff is bizarre, but there's a lot of physics that works based on this. I mentioned earlier that Newton created calculus so that he could do physics. There's a lot of physics embedded here. Lots of rates and accelerations and speeds. It's good stuff. That'll do it for this particular video. We got another one coming about areas. Stay tuned for that.